All right, let's talk about graphing logarithmic functions. Now, if that sounds a little intimidating, don't worry. There's one simple idea that connects these graphs to something you probably already know pretty well: exponential functions. Let's dive in.
It really all starts with just one question. Picture that classic exponential graph, the one that swoops up really fast. Now, what do you think would happen if you reflected that curve in a mirror, one that's placed perfectly on a diagonal line? Just hold on to that thought for a second.
So that mirror line we're talking about? In math, that's the line y equals x. And when you reflect any function across that specific line, you're actually finding its inverse. And an inverse function is exactly what it sounds like. It just undoes or reverses whatever the original function did.
And here it is, the big reveal. The logarithmic function is the inverse of the exponential function. That means the graph of a logarithm is quite literally the mirror image of an exponential graph. So if you can sketch y equals b to the x, you've pretty much got this. The connection is that direct.
Okay, so let's actually take a closer look at this reflected shape. What are the key features, the anatomy, that we need to spot on every single log graph?
The number one most important feature of a basic log graph is its vertical asymptote right at x equals 0, which is just the y-axis. The curve is going to get closer and closer and closer to this line, but it will never, ever touch it. This is our starting boundary, our wall.
And all these other features are tied right back to that asymptote. Because of that wall at x equals 0, the domain has to be anything greater than 0. The range, though, that goes all the way from negative infinity to positive infinity. Now, every single parent log graph will cross the x-axis at the exact same spot, the point 1, 0. And here's a super handy shortcut. The point b, 1, where b is just the base of your log, is always on the graph.
All right, theory's great, but let's actually see how this works. We're going to walk through a couple of examples, starting with the basics and then getting a little more interesting. We'll kick things off with the classic y equals log base 3 of x. To really get a feel for this graph shape, the best way is to just plot a few well-chosen points. So how in the world did we pick these x values? Well, here's the trick. Don't pick x values. Instead, pick easy y values first and then work backward. Ask yourself, 3 to the power of y gives me what x? So 3 to the power of negative 2, that's 1/9. 3 to the power of 0, that's 1. 3 to the power of 1 is just 3. See? By picking simple powers, we get x values that are easy to plot. Connect those dots, and there's your log curve. Okay, time to level up. What happens when we start shifting and moving the graph around? In this case, we have a log base 2 that's been moved from its original spot. We just follow a simple process here. First, always identify the parent graph, which is y equals log base 2 of x. That x minus 3 inside the parentheses, that tells us to shift the entire graph 3 units to the right. Then the plus 1 on the outside tells us to shift it 1 unit up. And here's the crucial part. That vertical asymptote we talked about, it moves too. It slides right 3 units along with the graph. So our new boundary is at x equals 3. For our last example, let's throw a reflection into the mix. See that negative sign out front? That's going to flip the whole thing upside down. We also need to figure out exactly where the new x-intercept is.
Let's just take it one step at a time. We start with our parent graph, y equals the natural log of x. That negative sign flips the whole curve over the x-axis. Then the plus 2 shifts that flipped shape up by 2 units. Now to find that new x-intercept, we just need to figure out where the graph's height is 0. So we set y equal to 0 and solve the equation. 0 equals negative ln of x plus 2. A little bit of algebra gets us to ln of x equals 2.
Now how do we solve for x when it's stuck inside a natural log? Well, you have to use its inverse, which is the number e. We basically make both sides of the equation an exponent on top of e. That cancels out the ln, and poof, we get our answer. X equals e squared. So our x-intercept is precisely at the point e squared 0, or about 7.39, 0.
Once you see the pattern, graphing these isn't so bad. But there are a couple of really common traps that are super easy to fall into. Let's make sure we know how to avoid them.
This is the big one. So many people mix up their asymptotes. Just think back to that mirror image idea. Exponential functions shoot up, but they flatten out horizontally, so they have a horizontal asymptote. Since log functions are their reflection across that diagonal mirror, they have to flatten out vertically. That means they have a vertical asymptote. They're total opposites.
And here's the other big pitfall, forgetting that when you shift the graph left or right, you also change the domain. Remember, you can't plug a negative number or 0 into a basic log. So if you shift the whole graph to the right by h, you're also shifting that no-go zone. Your new domain is everything bigger than h. It's an easy thing to forget, but it's super important.
So you might be thinking, okay, cool, curves. But why does this actually matter? Well, it turns out these strange curves are absolutely essential for making sense of the world around us.
Think about things like the power of an earthquake or the loudness of a sound. The difference between a whisper and a jet engine is massive. A normal linear scale just can't handle that range. That's where log scales come in. A magnitude 6 quake is 10 times stronger than a 5 and 100 times stronger than a 4. Log scales tame these gigantic numbers and put them on a simple scale we can actually understand and work with.
And that brings us right back to where we started. If you take away just one thing from all this, let it be this. Stop thinking of logarithmic graphs as some weird new thing. They're not. They are simply the other side of a coin you already know. They are the reflection, the inverse, the mirror image of exponentials.
So I'll leave you with a question to think about. If logarithms can help us see the vast energies of earthquakes and map the brightness of stars, what else is out there? What other invisible patterns are hiding in plain sight, just waiting for us to look at them through the right kind of mathematical mirror?